Right. Happy Thursday. Thursday, week 7. We're in chapter 8. So, chapter 8 is something like very foundational for 9 and 10. And as I said before, 9 and 10 are my favorites. They're really kind of awesome. But chapter 8 is the foundational stuff for that. Hopefully, you've already taken your test so you won't be confused with the chapter 8 stuff when you're going in to take the test on 5 through 7. So hopefully you've got that done since that is due tonight. Um, I know I had something else. Oh, don't forget that the data is due on Tuesday. You do not, if you are start working on it and your topic isn't working, it happens sometimes. You don't have to check with me to change your topic. I mean, you can if you want, but you don't have to. The basically these assignments, the data, sending in your data and the project proposal and all of that, those are basically just to make sure that you're working on your assignment for a while rather than waiting for the last minute. Nothing worse than realizing, 2 hours before the final project is due that, hey, I haven't even started my final project. So having a couple of assignments leading up to it helps you to be thinking about it and working on it for a little while rather than starting it last second. Because I mean, I know that, yeah, I've been teaching long enough that I know that if given the chance, a lot of people will wait till the very last minute. And I don't want, it's 15% of your grade. I want to make sure that you're turning in something quality that'll give you the grade you want and deserve. So I'm hoping that we end up with some really great projects. Okay, so today we are going to be dealing with chapter 8. We're going to be talking about sampling distributions of mean and proportions. We're going to start with proportion and we're going to work on mean after that. Actually, backwards. Start with mean and work on proportion. I get those mixed up in chapter 8 because in chapter 9 and chapter 10 they swap them and we do proportion first and mean second. So I don't know why they change it. Anyway, that's what we're going to do, and I'm going to explain to you what a sampling distribution is. It's a way to kind of get more accurate data without knowing the population. So we're going to just jump right into it. Okay, so what a sampling distribution is, it is to you figure out your sample size. So you take a sample, let's say sample size of 5 or a sample size of 10, and you take as many samples as possible of that sample size. So if my population was 5,000 and I was had a sample size of 100, I would take every possible sample of size 100 out of that population. Now, sometimes the population is way too big to do that. So we would just take a large number of those samples rather than every single possible one. So, like for example, if we're talking about the population of the United States, where we have, I don't even know how many, like 300 million people in the United States. I don't know what the actual number is. But say we have 300 million people in the United States and we're doing sample sizes of 100. I'm probably not going to take every single sample of size 100 in the United States, but we can take a lot of them. So our sampling distribution of mean would be each of those samples that we would take. We would find the mean of each of those samples. So taking all of these samples of size 100, you would find the mean of each of those samples. Then our new data set would be the mean of each of those samples. And I'm going to show you some examples to hopefully make it make sense. All right. So here's an example. The government wants to figure out the mean income of United States households. We can't survey every single household in the whole United States to find the mean. Therefore, we take a survey of 250,000 randomly selected households, and you figure out that the mean of those 250,000 is 72,641. Then you take another random sample of size 250,000 and you take the mean of those, 71,849. Then you do it again, 72,978. You continue to do this And then your new data set would be the means of each of those samples. So it's a way of looking at a lot of data by condensing it to the means of each of those samples. All right. So here's how we do it. Here's how you would take that. I am not going to test you on how do you take these samples or how do you do a sampling distribution. I just want to kind of give you an idea of what we've done. So you would take a simple random sample of whatever size you've chosen. You figure out what the mean is of the first sample. And then if it is a finite population, then you're going to keep doing it. You're going to keep getting those samples and calculating the mean of those samples until all possible samples have been obtained. Once you've obtained one sample, you can't obtain the exact same one a second time. Now, it might have some of the data values in common, but it's not going to be an exact identical sample. You're going to take every possible sample of whatever size n you have, if it's a finite population. Now, we would not consider like the population of the United States. Technically, there's 300 million people, but that as far as sampling goes, we would pretty much not consider that a finite population. Kind of like we're gonna have an example in a minute of using samples of pennies. The number of pennies there are in the US, we wouldn't consider that a finite population because it would be pretty much impossible to take every single sample of size 100 or size 5 or whatever. Finite population is one that's a little bit easier to take all the samples of. Like the high school I work at, I think we have 300 students. So if I was doing like a sample size of 10, then I definitely could get every single sample of size 10 of that population. Whereas something larger, it would be much more difficult. All right. So here's kind of I want to show you what this looks like when we start comparing the means of each of these. So I'm going to show you what this looks like and how it helps us to more accurately figure out what the population mean of something is and what the population standard deviation is. It's a better like estimate. So the weight of pennies minted after 1982, they're approximately normally distributed. We have a mean of 2.46 grams and a standard deviation of 0.02. So we are approximating the mean of our population. So we're taking a sampling distribution of our means, of our sample means, by taking 200 simple random samples. So those 200 samples are size 5. So we took 200 samples of size 5, and every set of 5, we found the mean weight of those 5. I'm going to show you what that looks like. All right. So here's one of my samples. I took 5 pennies, and I found the mean of these 5 pennies, the mean weight of these 5 pennies. So our mean weight, I guess I can use my pencil. The mean weight of these five pennies was 2.479. And then I would take another sample, would do this 200 times, randomly select 5 pennies, weigh them, find the average weight. Take 5 more pennies, weigh them, find the average weight. We're going to write those down. Each one of those means, write down those means of those 5 pennies. We're going to do that 200 times. So now instead of whatever 200 times 5, so instead of 10,000 pennies, we're going or 10, sorry, instead of 1,000 pennies, we're going to be looking at 200 data values instead of 1,000 data values. It makes it a little bit easier, and it helps us to estimate the population. So let me show you what this looks like. So right there, I took 200 samples of size 5, and I found the means of each of those 200 samples. So now, these are all of the means. These values that I have in here, these are the means of each of those samples. The nice thing about this is that they're going to be closer together. So our standard deviation, just a second here, was 0.02 grams. But now when I'm looking at the means as my data set, my standard deviation is going to be much smaller because I'm looking at how much does the mean of each 5 pennies differ from each other. My standard deviation is going to get smaller. You're going to see that in a second. I've got some graphs and all that lovely stuff. So let's take a look. So the mean of the 200 sample means is 2.46, which is the same as our population. The standard deviation of our sample means is this number right here, 86 10,000ths. So this is much, much smaller than our 0.02. It's much easier to estimate the average of a sample with this teeny tiny little standard deviation. So let me show you what the histogram looks like. Here we go. So this is a histogram of our means of each of our samples. And it's not the most beautiful bell curve. In fact, it looks like it's just slightly skewed, but it still looks pretty much normal. And especially since our population is normal, this looks normal as well. But I'm gonna increase the sample size and we're gonna see what happens. So we were trying to figure out what the role the sample size plays in our standard deviation because we saw that the average, that the mean of all of those means was the same as our population. So that's probably not going to change with changing our sample size. But let's see what happens with the standard deviation. This right here is important. Write this down. You will be asked this. I think you get asked this on the quiz. Definitely in a homework assignment. You get asked what happens as the standard sample size increases. So as the sample size increases, your standard deviation is going to decrease. I'm going to show you what that looks like. But as our sample size increases, the standard deviation is going to decrease. So this is something that you're going to want to keep in mind. I'm not going to ask you it on the next test, but definitely homework, possibly a quiz. I can't remember if a quiz asks you or not, but definitely in the homework. So let's take a look. So I'm going to use a sample size of 20 instead of the sample size of 5. So I still have the mean of 2.46, and I'm pretty darn sure that if my population mean is 2.46, that a sample size 20 is not going to change what happens with our sampling distribution. But let's take a look at what happens with the standard deviation. So take a look here. When we had a sample size of 5, our standard deviation was 0.0086. We're basically about half. With a sample size of 20, our standard deviation is about half. So it is much, much smaller. So all of our means are even closer together. And look how much prettier the bell curve is. That bell curve is much prettier than it was when we had a sample size of 5. It looks much nicer, much more bell-shaped, a lot less skewed. So this is good. We like this. Much smaller standard deviation there. So bigger sample size is good if you can. If we can do a bigger sample size is good. All right. So we have a way to calculate the standard deviation without actually finding the mean of all of these means, or the mean of all of these samples, and then taking the mean of the means and calculating the standard deviation of those means. We have an actual way to calculate it. So we have a formula right here. So the new standard deviation, this is what I call it, the new standard deviation or the standard error. They mean the same thing. The standard error of our sampling distribution is the population standard deviation divided by the square root of the sample size. Since our standard deviation gets smaller as our sample size gets bigger, this new standard deviation or this standard error depends on the sample size. One thing important to note, and we saw this with our sample of pennies, is that the mean of our sampling distribution is going to equal our population mean. So the mean will just be whatever our population mean is, even though it's indicated with mu sub x bar. And then our standard deviation, which is indicated with sigma sub x bar, is this population standard deviation divided by square root of n. So you will be asked, I believe in your homework, most of the time they refer to it as standard error. They do occasionally ask you for standard deviation of your sampling distribution. So either way, so I sometimes will call it the new standard deviation. Sometimes I'll refer to it as the new standard deviation, but it's also referred to as standard error. I'm going to show you how close it is to the actual. We're going to actually calculate with the pennies and show you how close it is. All right, let's do that here. So with the sample size of 5, we take our population standard deviation, which was 0.02, divide it by the square root of 5, and we get 0.0089. That is super close to what we found in our example, what the actual was. It is 3/10,000ths off. So as long as you're not building a space shuttle, 3/10,000ths is okay. It is super, super close. And when we changed it to 20, so we calculated the standard error for when it is 20, and we got exactly the same thing. We got exactly the same as the actual standard error, the actual standard deviation of our sampling distribution. We're going to do a couple of these calculations, but any questions before we do these calculations? All right. So this is important, and I know that this is on a quiz. If the random variable x is normally distributed, then the sample mean is also normally distributed. Now, there's one other thing that you need to look at, and this is, I believe it's on a different slide, but I'm going to write it here also. If our random variable x isn't normally distributed, then our sampling distribution becomes normally distributed if our sample size is large enough. And I'm going to write this down. If the population or the random variable is not, I know this is on another slide, but this is a good time to write it, normally distributed, then the sampling distribution becomes normal if the sample is large enough. The sample size that you need to look for is n would needs to be greater than or equal to 30. This is called the central limit theorem. I am not requiring you to remember that it is the central limit theorem. But if you just remember that the sample size needs to be large enough, the sample size needs to be greater than or equal to 30 if our random variable is not normally distributed. If you don't remember it's the central limit theorem, that's okay. If you do, that is also okay. Give you a second to write it down and then we'll move on. And it's probably the very next slide, but that's okay. I just like it all together. This is a question on one of the quizzes. All right, I'll move on. And my handwriting is really bad there. All right. So we're going to calculate the mean and the standard error, aka the new standard deviation. So an IQ is a measure of intelligence and it comes from a standardized test. The scores on the test are approximately normally distributed with a mean of 100 and a standard deviation of 15. We're going to find the mean and the standard deviation of the population with a sample size of n equals 9. All right, so my sample size is n equals 9. Remember that our mean is always just going to be what the population mean is, which is 100. So your mean is just the population mean. Our standard error or new standard deviation is the population standard deviation divided by the square root of the sample size. Thankfully, this math on this one, super easy. We don't even need the calculator because it's just 15 divided by 3, which is 5. They're not always going to be that pretty. So our mean is 100 and our standard error is 5 for our sampling distribution of sample means. You're going to do the next one. Okay. I want you to give this one a shot. I want you to find the mean and the standard deviation, then we're going to do the probability together because I don't think this gave us a probability. No. So I want you to find the mean and the standard deviation on this one, and then we will do the probability together. So the weights of pennies minted after 1982 are approximately normally distributed with a mean of 2.46 grams, standard deviation of 0.02 grams. We want to know the probability that in a simple random sample of 10 pennies minted after 1982, we obtain a sample mean of at least 2.46 grams. So all I want you to find is the mean and the standard deviation using what we just did. If you get stuck, it's okay. We're going to go over it together. Right, so our mean is the same as the population mean. The standard deviation is the population standard deviation divided by the square root of the sample size. This one's not quite as pretty of a number. I have approximately 0.0063. How'd we do? Yes, good job. You want to put the 2 on the end? We'll throw the 2 on the end. Yay, good job. All right. So we already have the tools to find the probability. We already have those tools. The probability, what we are going to use for that probability is just normal CDF. Everything is going to look the same, except the standard deviation we are going to use is the one we just calculated. So everything else is going to be the same because the way that that 10 pennies is considered in there is in that standard deviation. So we're just going to use our normal CDF. So it'll be normal CDF, and it says at least, so it's greater than. So it would be 2.465, comma, 1E99 because it's greater than. You would use the mean given, 2.46, and then the standard deviation we just calculated. So this is going to give the probability of if I took a sample of 10 pennies, what is the probability that the sample mean, the mean of those pennies, the average weight of those pennies is 2.465 or greater. So we're just going to do that in our calculators, the normal CDF. Let's see. Look at you already having the answer. I haven't done it yet. I believe you though. If I put it in my calculator correctly, I agree with you. Yep. Our probability. So the probability that our X bar is greater than or equal to 2.465. So the probability that our sample mean is greater than 2.465 is exactly what you have, 0.2 0.2144. So the probability we just found is that the average weight, or that the average weight of those 10 pennies is greater than or equal to 2.465. That's what we just found. And it's about 21% chance that it is greater than that. Questions on this? Right. So this is what it would look like on it's the same math we just did, except for what they do. And I just, you are more than welcome if you want to convert everything to z-scores. Their answer looks a little bit different because they converted to z-scores, but I prefer doing this rather than converting to a z-score. They converted it to a z-score, so their answer is slightly off, but it doesn't make sense to me to convert it to a z-score. But that's just me. So your answer should be the 2.2144 because we didn't do z-scores. Remember, z-scores are rounded numbers, and so we end up with a slightly different answer. All right, let's do another one. I want you to give this one a try without me, and I will work behind you quietly. So the IQ of humans is approximately normally distributed with a mean of 100 and standard deviation of 15. Compute the probability that a simple random sample of size 10 results in a sample mean greater than 110. So we're looking for the probability that our sample mean is greater than 110. So give this a shot, get as far as you can. If you get stuck, go ahead and just stop and wait until I work behind you. I'm going to work quietly behind you, give you a head start. Let's see. My answer is a little bit different than yours. I wonder if I did something wrong. Oh yeah, I did. I left a number out. I was like, something's weird here. Yeah, I got the same thing as you. So there's about a 1.8% chance that if you randomly selected 10 people, that their average IQ is greater than 110. That's what this is saying, that if I randomly took a sample of 10 people, that their IQ would be greater than 110. It's about 1.8% chance. So this would be unusual. It would be unusual to get a sample like that. Questions on this? All right. So I already talked about if we have a non-normal sample. I already kind of mentioned that back there. So for example, right here, rolling a dice, the sample is not normal. So our mean is 3.5, which makes sense because it's right there in the middle ish. And the standard deviation is 1.708. So that is the population standard deviation of our rolling a dice. So this is not a normal population. So let's take a look at what happens as our sample size gets bigger. So we see sample size of 1, which really isn't a sample, but showing that if I'm doing one dice roll at a time, this is what my distribution is going to look like. So I'm going to show you what it's going to look like with a sample size of 4, then a sample size of 10, and a sample size of 30. So if I'm taking 200 samples, first of size 4, then of size 10, then of size 30, let's take a look at what happens. So here's size 4. Now, this is interesting. It's better than the uniform distribution we have. It is a little bit skewed, but it is better than the uniform distribution using our sample size 4. Let's take a look with a little bit bigger. Sample size 10. This is looking better. This is definitely looking better. Now let's take a look at 30. 30 is a nice, pretty normal curve. It is almost perfect normal curve, almost perfectly bell-shaped. So one of the reasons that we use sampling distributions is because most of our methods of analysis, we have to have a normal distribution. Most of the things that we do, we can't do unless our distribution is normal. And if I have a variable that the random variable itself is not normal, I can use sampling distribution to make it normal. By taking larger sample sizes, it makes that normal. So then I can do all of the math that I know how to do with it. So this becomes a nice bell curve. So now I can use all of my methods of analysis because now it is normal. So once again, if your population or if your sample is a size 30, when you have a not normal population, it becomes normal. I think that's on my next screen. There we go, central limit theorem. So the shape of the distribution becomes normal as the sample size increases regardless of the shape of the population. Now, my mean of my sampling distribution is still going to be the same as the mean of the population, but the standard deviation is going to use this little formula that we have. And we're going to be using this formula in chapters 8, 9, and 10. So it's a good one to keep on hand because we're going to be using it in all 3 chapters. So we still use our standard error or new standard deviation, and we still use the population mean as the mean of our sampling distribution. But if our population isn't normal, the sample size needs to be greater than or equal to 30. Now, I believe that some of the examples in the homework, and I think even on the next test, don't tell you whether or not the population is normal. Just still do the math on it. I mean, just still do it, but just somewhere in the back of your head, say, this they should have told me whether it's normal or not. But if you were doing your own study somewhere, you never know. Out in the wild, you may end up doing your own study. If you do, using sample sizes of larger than 30 is going to help you. So this doesn't say what sample size it is, but I'm going to write it if your sample is greater than or equal to 30. How this isn't some magic number. It is just the number that statisticians have landed on because it seems to be common that once it hits 30, it becomes normal. And so it is the number that they use. So it is just our rule of thumb there. Any questions? All right. Okay. So on this right here, when it tells you to describe the sampling distribution of sample mean, all it wants is the mean and the standard deviation. So if it says to describe it, it's looking for the mean and the standard deviation. So I want you to give this one a shot. So it says the mean time for an oil change at 10-minute oil change joint is 11.4 minutes with a standard deviation of 3.2. With letter A, you're just finding the mean and the standard deviation. Letter B, you want to find out the probability that a sample size of 35 randomly chosen is less than 11 minutes. Let's go ahead and give this one a shot. I will work quietly behind you. Okay, let's see what you got. All right, good. And I got the same thing, 0.2298. I got the same thing. Good job. How'd we do, everyone? So there's about a 22, or say about a 23% chance that if you took a random sample of 35 oil changes, that the average would be less than 11 minutes. So a reason for using this kind of math, so if they're saying, hey, my average time for an oil change is, this is 10-minute oil change joint, even though I average 11.4 minutes, then they would taking one random sample, one car, the you're more likely to end up with an outlier or something that is more unusual. But taking a sample of 35, it's a like better picture of what your overall would look like. So saying, I'm going to take this sample of 35 cars, randomly choose 35 cars, and take that average and see how that compares to the average that you claim. And so they randomly select 35 cars, and the average of those 35 cars was less than 11 minutes. And 23% chance that's not unusual. So it kind of just gives a more accurate picture of overall performance of this oil change place, if that makes sense. Right, I believe that's the end of that's the end of 8.1. Any questions on 8.1 before we jump into 8.2? All right, so don't stick all of the knowledge in your pocket, but put the formulas in there because we're not going to use that standard deviation formula. So put that in your pocket, but keep the sampling distribution knowledge in your head. And we're going to jump into 8.2. So we've dealt with point estimates before. We didn't call them point estimates previously, but we've dealt with them before. So a point estimate is basically the number of successes that we have in a sample. So we've done this before with yeah, several, like when we did relative frequency or when we did our experimental probability, when we did things like that, we did the same math, we just called it something different. So a point estimate is when you take the number of successes or the number in, the number of individuals in a trial that have a certain characteristic and divide it by the total number of trials you had or by your sample size. So p hat means that anything with a hat, you may recall this from when we did regression, any variable with a hat means that it is an estimate. If a variable has a hat, it's an estimate. So p hat is an estimated proportion. So it's our sample proportion. So if I took a sample, say I took a sample of 100 and I'm looking for how many households have cats, I'd say, okay, out of these 100 people, 37 of them, those households had cats. I'd put 37 over 100 and 0.37 would be our p hat. That would be our sample proportion. So a sample proportion, it's a statistic that we use to estimate our parameter, which is our population proportion. So we're estimating the entire population based on our sample. So that's what a p hat is. So we just say p hat instead of sample proportion because p hat's easier. All right. So right here, we have a Quinnipiac poll. 1,745 registered voters were asked in 2008, were asked whether they approved of the way George W. Bush was handling the economy. 349 responded yes. We're going to get a point estimate. So point estimate is our p hat. So we just take the 349. Oh, that is really ugly. 349. Still ugly, but I'm just going to leave it over 1745. We put that in our calculator to get our sample proportion. So it's 0.2. So about 20% at that point believed that or approved of the way that George W. Bush was handling the economy. All right, let's do another one. So Opinion Dynamics conducted a survey of 1,000 adults. Are you currently on some form of low carbohydrate diet? Of those survey, 150 said that they were. Once again, we're going to find our p hat. So p hat, there's 150 said that they were on some sort of a low carb diet. Just put that in our calculator. So that's about 15%. And I don't know why I put that in my calculator because that one was an easy one. Because sometimes we just put simple things in our calculator. It's really funny because occasionally I'll pick up a calculator after like one of my AP calculus students have used it and it'll have something in it like 14 divided by 2. Sometimes we just do that. Sometimes the easy math just falls out of our brain. I'm sure we've all had that issue. All right. So let's talk. I want to show you what goes on. This is basically the same type of things we were doing with our sampling distribution of mean. We are now going to look at sampling distribution of proportions. So proportions, we usually use those when our data is categorical. So when we have categorical data, a lot of times we'll just look at the proportion of our sample that has a certain characteristic. So in this case, in 2008, 42% of registered voters believed that gay and lesbian couples should be allowed to marry. We're going to look at the sampling distribution of proportions for size 10, 50, and 100, and we're going to have some histograms here. So it's the same basic thing. We took a whole bunch of different samples of 100, and we found all of those proportions. So let's take a look. So notice when we have a sample size of 10, we look like we're a little bit skewed to the right. And take a look at my mean and standard deviation here. So our mean, we were at 42%. This mean is showing 42.6%. Standard deviation is 0.160. A little bit bigger. size 50. This is a little bit better, a little bit more proportional, a little more symmetric. Our mean, 42.6, it's getting closer to our 42%. Standard deviation is getting smaller. We're going to look at our size 100. This is pretty close to a nice, beautiful bell curve. I mean, there's a little tiny tail over here, but it doesn't look like anything to worry about. Our mean now is exactly the population, and our standard deviation is super small. One of the nice things about this is that when we're dealing with proportions previously, before using sampling distributions, the only way that we could analyze using categorical data was with our binomial probabilities. And I know how much y'all love the binomial probability distributions. But now, by using sampling distribution of proportions, we can just, it's basically converting it to something that we can now use our normal CDF. So it's kind of like, it's almost like changing our units so that they're common so that we can use normal CDF. Not actually, but kind of the same way. It puts us in a way that we now have a mean and standard deviation, and we now can use our normal CDF to do our analysis. And I don't know about y'all, but normal CDF is much easier for me than binomial probability distributions. Even though I do like the binomial stuff, but this is also a little better because we have these big sample sizes. We have a lot of samples, and we can find the probability of getting a full sample with a certain proportion. So it makes it a nice estimate of our population. So, all right. So this is going to be important stuff as well because I believe something like this is going to be written on your on one of the quizzes, and something else is going to come up that we've seen before, and I'll talk about that in a second. So as our sample size increases, the shape of our sampling distribution becomes normal or approximately normal. So as we get a bigger sample size, we become normal, very similar to the mean, correct? As our sample size gets larger, the mean of our sampling distribution of the proportions is the same as the population proportion. So whatever our population proportion is, that's what we're going to use for the mean. Our standard deviation is going to get smaller as the sample size gets bigger. Same with dealing with means. As the sample size gets bigger, our standard deviation is going to get smaller. So thankfully, these are the things that are the same with the mean and the standard deviation. All right. This is the things that are important right here. This right here, you're going to be asked about this on a quiz, and you need to once again use this piece right here. The shape of the distribution of our p hat is approximately normal if NP times 1 minus P is greater than or equal to 10. This should be familiar. We've done this before. Our shape becomes approximately normal if NP times 1 minus P is greater than or equal to 10. Our mean is going to be the same thing as the population proportion. And this is how we are going to calculate the standard deviation or standard error right here. This is how we calculate it. You take the square root of the probability of success times the probability of failure divided by the sample size. Depends on the sample size because remember, the standard deviation gets smaller as our sample size gets bigger. So our standard deviation depends on that sample size. So don't forget this formula. It does look a little bit different than the formula that we used for our binomial probability distributions. It looks a little bit different, so just set that one aside. Don't go back to that right now. So we're going to use the square root of P times 1 minus P divided by N, and we're going to be using this for the next 3 chapters. So all 3 chapters, we're going to be using all of the information on this page. It's going to be used for the next 3 chapters for 8, 9, and 10. So they're not going to be you'll be getting a couple of new formulas, but nothing crazy. All right. So, but remember this right here for your quiz. Okay. Another important thing, remember when we were talking about independence and dependence? We were talking about that. In fact, we went over that in our study session on Tuesday. So, in order for our samples to be independent, our sample size, if we're sampling from a finite population, our sample size needs to be um, less than 5% of the entire population. So if I have a school of 300 children, I cannot take sample sizes of 50. I'd need to take sample sizes of 15 or fewer. So our sample size needs to be less than 5% of our population. This tells us whether or not it's independent. So this is right here is the test for independence. I know it says it in that paragraph, but test for independence. That's the test for independence. This is test for normal. So that's the NP times 1 minus P greater than or equal to 10. That's our test for normal. And the sample size being less than 5% of the population, that's our test for independence. Now, this is for a finite population. It's really easy when you're talking about like the population of the United States, because pretty much any sample size you choose is going to be less than 5% of the population. I still want you to tell me that it's less than 5% of the population, though. So no matter what, even if we determine that it's not normal, we're still going to use this for our standard deviation. So it's still going to be the standard deviation. So these are the things you're going to test ahead of time. So if it's asking you to describe your distribution, so if in your homework it says describe the sampling distribution of proportion, tell me it's less than 5% of the population. Tell me that NP times 1 minus P is greater than or equal to 10. Tell me that your mean sub p hat equals whatever the population proportion is, and then show me the standard deviation. Those are the things in your describing your distribution that I want to see. All right. All right. This is just what we're so according to a time poll conducted in June of 2008, 42% of registered voters believed that gay and lesbian couples should be allowed to marry. We're going to obtain a simple random sample of size 50 and determine whether or not um, determine which voters believe that they should be allowed to marry. So we're going to describe our sampling distribution. I'm going to be up on top of that purple part because I need more room. So by starting, first thing I'm going to test for is independence. So 50 is less than 5% of my population. So it is independent. 50 is definitely less than 5% of the entire population of the United States, or registered voters. Then we're going to test for, is it normal? So my NP, so my, sorry, P times 1 minus P, yeah, sample size. So N times P, which is 0.42, times 1 minus 0.42. I'm going to put that in my calculator. NP times 1 minus P, 50 times 0.42 times 1 minus 0.42. I have 12.18, which is greater than or equal to 10. So we're normal. So I did NP times 1 minus P. I got 12.18. So that means that we're normal, that this is a normal distribution. Perfect. The mean, mu sub p hat, is just 0.42. The mean sub p hat is 0.42 because that is my population proportion. Our standard deviation sub p hat is the square root of 0.42 times 1 minus 0.42 divided by the sample size, which is 50. If you're careful with your parentheses, you can put the entire thing in your calculator at once. So you just got to be careful. You can also do it piece by piece if you want to. So I have approximately 0.0698. So my standard deviation is about 0.07-ish. So this is how you're going to describe your sampling distribution of sample proportions. Show me it's independent, show me it's normal, give me the mean, and give me the standard deviation. That is how we describe the distribution. Questions on this before I move on? All right. They do it here also. I just feel like doing it, actually talking it through while I math it out generally is more helpful than just giving it to you on the screen. However, if you were reviewing this on your own, yeah, see, I have in the past when I first started teaching this, I'd just be like, there's all the math, and I would talk through what's already written there, but it doesn't seem to resonate as well. So I'm glad you agree. So this is just the description. We haven't done any probabilities with it yet, but this is the description we're looking for if it says to just describe it. Usually it's a box. Usually it's just a box in your homework. They give you a big box to type in, and it looks for specific numbers and things and marks you correct or incorrect based on specific things it looks for. And if it marks you incorrect, I generally go in and take a look at it for ones that are marked incorrect because sometimes people just type really poorly. So it's not something that's manually graded in your homework, but I usually pop in and take a look at it just in case, because sometimes my open math is an imperfect thing, as you've probably noticed. So I try to go in and look at it after the due date. All right. Now we're going to do some probabilities. Actually, this one doesn't have a probability. I'm just going to jump ahead to a probability. There we go. All right. According to the Centers of Disease Control and Prevention, 18.8% of school-age children aged 6 to 11 were overweight in 2004. In a random sample of 90 school-age children, what is the probability that at least 19% are overweight? We're going to talk about letter B afterwards, but let's do letter A first. Okay. So first thing I'm going to look at is independence. So we have a sample size of 90. So 90 is less than 5% of our population. So I'm just going to put a check mark. It's independent. Then I'm going to look for normalcy. Is our sampling distribution normal? So it's going to be NP times 1 minus P. So we have 90 school-age children times 0.188 times 1 minus 0.188. Is it less than or equal to or greater than or equal to 10? Let's check. 90 times 0.188 times 1 minus 0.188. Yep, we got 13.74, which is greater than or equal to 10. I'm just going to put a check mark once again to show, yes, it's normal. Good. That's important. Now I need to calculate my mean and my standard deviation. So I'm just going to do this down here at the bottom. So the mean sub p hat is 0.188. Standard deviation sub p hat, square root of 0.188 times 1 minus 0.188 divided by 90. Once again, careful with your parentheses. divided by 50. I have 0.055. All right. So I have my mean and standard deviation. So we're looking for the probability that I get a p hat that is greater than or equal to 0.19. That's what I'm looking at. I'm looking for the probability that I take a sample of 90 kids and the proportion of those kids that are overweight at 19% or more. That's what I'm looking at. So previously, when we did binomial probability distributions, we looked at what is the probability we randomly choose, or that like 5 out of 90. So I mean, technically, I could still use binomial probability distribution because I could say sample size 90, 0.188, and then figure out what number of 19, what number out of 90 is 19%. I could do all of that. But in my opinion, this is a little bit easier. So 0.19, because we're doing greater than 1E99. Our mean is 0.188 and our standard deviation 0.055. I'm going to put that in my calculator, see what we got. 9, comma 1E99, 0.188, 0.055, enter. I can't fit it there, but I'm going to just put it right down there. Yeah, that's ugly. You're getting a different number for standard deviation? Right, it's possible I did something wrong. Let me try it again. You go ahead and try it again also. So let me actually, let me get to my calculator. Okay. So square root, parenthesis, 0.188 times, parenthesis, 1 minus point, whoa, that's not a point, 0.188. I'm going to close both parentheses, divided by 50. This is what mine looks like. And then hit enter. You need to make sure the entire numerator is in a parenthesis. Oh, okay. Oh, it is 90. That's my problem then. This is my error. Good job. Thanks for catching my error. I don't know why I put 50. So I'm going to have a different number than you. Or I have a different number here. Okay. I did the same. It was my error. Thank you. I'm so thankful when y'all do it in your calculator while I am, because I am an imperfect being. Okay. There we go. I'm going to redo it. Redo my normal CDF here. Thank you so much. Yet another example of your math teacher is human. I play that game way too much. Okay. So my probability, so this probability right here, so that probability that p hat greater than or equal to 0.19, so approximately, did you get 69%? I want to make sure that I didn't do anything wonky there. Okay, so this is now saying, suppose a random sample of 90 school-age children aged 6 to 11 results in 24 overweight children. What might you conclude? So you need to kind of read between the lines on questions like this. So what we need to do is we need to find the probability that we get 24 or more overweight children. So probably what I would do, I'm going to jump back over to my calculator here. I would say I'm going to put I'm looking for greater than or equal to 24 overweight children. So remember that you can put math directly in here. I don't know if I think I showed you guys that before. You can put math directly in there. You don't actually have to calculate the p hat. You can if you want, but you don't have to. So you can just put the math in there and then do the 1E99. So the probability of getting 24 or more, I can put 24 out of 90 in the lower, and then my mean is 0.188, and then the standard deviation is 0.0412. You also got, you got, so you got a different probability than I did? Or you got a different, do you get a different standard deviation or a different probability? For the normal CDF? Okay, let me go back to my calculator and take a look at it. So I did 0.19. Okay, let me hit enter here. Do this again. So normal CDF, do 0.19 because we're looking at the 19% to 1E99, 0.188, and then 0.412. How come I got a different answer? I have the exact same thing in there. 0.0412. I don't know. So that's what I got also. So I don't know what I did wrong. I can't see it in my other calculator.
I will say this has happened to me before. I don't know what it is, but it is weird.
Yeah, I
Like,
don't know because I'm looking at my other calculator and I have all the correct numbers in there and it came out as the 0.69. So I don't know. We're gonna
the worst
but
part is for me, it happened during, oh, I'm sorry, go ahead.
no, go ahead. No.
It happened during the test, and I was like, oh, that can't be right. So I did it again. It did work out, but it took a couple extra minutes off of my time. I was like, oh, okay, cool. This
So
is happening.
this is why you write everything down is because if you write down like write down the whole normal CDF, like you write all of this stuff down in your work, all of this in your work, I'm going to look at that and say all of their work looks really good. It must have been a typo in the calculator. And then, I mean, you might lose a half a point, but you're not going to lose as much as if you didn't put that at all. So
Right,
the thing is if you show no work at all and you give me a wrong answer, I have no idea how you got it, and there's no partial credit because I don't even know what you did. But if you show this, because this is exactly what was in my calculator. So if you show this, I'm going to be like, okay, it must have just been a typo. And I'm sure you've all seen my comments. I mean, some of you have had typos, calculator typos on like your hand-in homework, and I'm right on there like, must be a calculator typo. And then I won't take off very much. But if you don't show me the work, I have nothing to go on. It makes it even harder with the online stuff because I have even less to go on. So yeah, that's why we show our work. Thank you so much for catching my errors. All right. So this one though, what I did was I put in, I'm going to go up here and I'm just going to clear that one because I want to look at this one. So what I did was I put in the 24 out of 90. Now you actually, if you want to calculate that p hat, you do the 24 over 90 and then put that in your calculator and I'm going to see what that is. And it would be 0.27, but and it's 0.26 repeating is what it actually is. But putting 24 out of 90 in your calculator, you're going to get more accurate. I'm going to see what get on my calculator with, instead of putting 24 out of 90, I'm going to put 0.27 and see how different that's going to look. 0.412. I'm going to see how different that looks. On my calculator with putting in the p hat of 0.27, I get 0.023. And here with putting in the fraction instead, I get 0.028. So it is just slightly off. Regardless, it's unusual. And that's really what we're looking at is we want to recognize the fact that we get an unusual value. So just a second, I'm going to write this down and then go to my next page. So even if you are using a calculator that doesn't have that menu, you can still put 24 divided by 90 in there before your comma. And it's just slightly more accurate. And I like slightly more accurate. So we got what I got 0.028. See. So this probability here, I got 0.028. So still no matter what, it's less than 5%. So we got so the what might we conclude? Basically, there's a lot that we conclude. We can conclude that since 2004, the obesity epidemic has gotten worse, and that we might want to rethink what the actual percent of school-age children their how the percent that they're overweight. So that is the what might be we conclude, or maybe we just got a sample with a lot of kids that are in food deserts or in poverty. We may just have had a sample like that. Most likely, when we get a result that is unusual, that doesn't match what our population is, most of the time we'll do another study. We will take another sample and see if it still is an outlier. If we take another sample and we end up with unusual values again, then we would say, hey, so something is wrong with our original data. Something's wrong with our 18.8%. And I don't believe that our homework asks you what you might conclude, but I know that a large number of people in our class are going into the medical field. So if you're going into the medical field and you are doing studies like this, you're going to be looking at old studies like 2004 and doing some calculations on them, or even going into business and be like, you know, my sample's showing really unusual. Something probably isn't correct with the original data that the CDC gave us. Something isn't right. Our actual numbers these days must be higher. That's just kind of what, you're got to be thinking about, is the original data correct? Because my sample here is highly unusual. Is the original data correct? And that's kind of where we're going with number B, is just to try to be like, what kind of a story does this tell me? What does this cause me to do? It causes me to study further. And anybody dealing with statistics, you know that you just never stop studying things. All right, we've got another example, and I want you to try this one on your own, and I'm going to work. Oh, this is all exactly what we just did. Okay, so oh, we did all of that. Okay. What might you conclude? Did they give a conclusion? Say we would only expect to see about 3 samples in 100, resulting in a sample proportion of um, of our p hat. It is unusual that if the true population proportion is 0.188. They didn't go to higher conclusions than that, but we as humans would take it farther rather than this, generic thing the textbook does. As humans, it would make us take a look at things. If we're studying obesity rates in children and our samples are unusual, you're going to start looking at things and you're going to start, using Michelle Obama's examples and being like, let's get some healthier food in schools. Let's teach some families about healthy cooking. Let's maybe try to make the healthy food less expensive. You'd be trying to figure out how to fix it. All right, we've got another example, and I believe this is my last slide. I want you to try this. This is exactly the same thing that we just did. I want you to try this on your own, and then I will work quietly behind you. So, according to the National Center for Health Statistics, 15% of all Americans have hearing trouble. In a random sample of 120 Americans, what is the probability at most? So that's 12% or less less than 12% have hearing trouble. What's that probability? Suppose a random sample of 120 Americans who regularly listen to music on headphones results in 26%, or 26 of them having hearing trouble. What might you conclude? So go ahead and try both of those, and I'm going to wait a little bit and then work quietly behind you. You don't necessarily have to on your own do the 5% thing in the NP1 minus P greater than or equal to 10, but it's good practice if you want to. Let me see here. You are working faster than me, that's for sure. Got the same thing as you there. Yay! Let's see if my calculator's nice to me. Got a different number than you. I could be wrong though. Anybody else for letter A? Is that the 0.2167? Is that what you got for letter A? So I think I have a different answer. I have a different answer. That's what I got, Rebecca. That's the same thing I got. Ari, check your normal CDF and make sure that you didn't typo in there. Yep, see? You're trying to take over my title of typo queen. You can't do that. I'm the typo queen.
I will battle for it, by the way.
No, you cannot have it. That's my title. Okay. Greater than or equal to, and I would say 26 out of 120. So yes, you can calculate your p hat if you want, but I'm just going to use the fraction. So you do what you want, but I'm just going to use the fraction. Just put this in there like that. And we're looking for greater than or equal to because 26 is a big number. Did I put that in there right? 20, oh, I put 23 instead of 26. I'm like, something's wrong here. Okay, well, the heck is wrong with me? There we go. So here I got 0.02. Did y'all get 2% for B? Yeah, good. So in this case, you would talk about because the our sample here was 120 Americans that regularly listen to music. So we would probably conclude that that we believe that headphones causes hearing loss in people. Having regularly listening to music in headphones may cause hearing loss. Now, we never base our conclusion on one study. Anybody who's taken some science classes, you know that your experiment has to be able to be replicated. So not only do you have to have your simple random sample, you need to have this stuff up here on the top. We need to have that. You need to have all of there, there's all of these steps in the scientific method. Statistics is a science. Using the scientific method, your study has to be able to be replicated. So in this case, I would take a look at this and I would say, okay, um, I got this 2%. This would be really unusual if the 15% is true. So I would take another sample of 120 Americans who regularly listen to music in headphones, and I would see if they also had this, 26 out of 120 or a similar number. I would also want to see that because you can't just conclude it based on one study. This is not how the scientific method works. So you would have to say, okay, well, this tells me that I need to keep studying this. I need to keep doing this study. So this is just like the preliminary math that you would do in order to get that study. All right, any questions? We are completely done with the chapter 8. I'm going to go over a couple of homework problems, but before I do that, any questions here? All right, so I know that this in my opinion, chapter 8, except for a couple of the homework questions that are a little confusing, it's pretty light math as long as you can get the little formulas for the means and the new standard deviation. It's fairly light, but I'm going to show you there's a couple of homework problems that have given people some confusion. So I want to look at those before I set you free. All right. Okay, so let's go to the 8.1. I think that's where they both are actually. Okay, so now this one right here, this one is it's not difficult. It's just that gives people a headache. It's just kind of a pain because of where things are. So your standard deviation, this is the new standard deviation that this is asking for. It's mean and standard deviation. It wants the new one, but notice how it like doesn't show up right on the computer. So this is the new standard deviation. Then what you're going to put in the middle here is the mean. And these two boxes are each two standard deviations away from the mean. So you would take the new standard deviation, multiply it by 2, add it to the mean and put that there, multiply it by 2 and subtract it from the mean and put it right there. This wasn't one I was originally going to go over, but that's what you're doing here. Okay, there's a question. Where is it? Where is it? This one. This is the most common problem. I'm going to go to a blank screen and kind of draw this, and we're going to talk about it. So the drawing of this, I'm drawing it on my other screen while I'm talking to you. The diagram is the sampling distribution. This is a really ugly drawing on my paper. You'll see. So the sampling distribution is the drawing. You can see by looking at it that the standard deviation of the sampling distribution is 4 because this is the mean. You can see to get to one standard deviation away, it's 4. So you can see that the sigma sub x bar is 4. It gives you the sample size. you're looking for the population standard deviation. So all you're doing is taking the formula. I'm going to pop over to the other screen. You're taking the formula sigma sub x bar equals sigma divided by n, or square root of n. You're taking the formula and you're just solving for a different variable. So the 4 is your standard deviation of the sample mean. We're looking for sigma, and my sample size is 49. Now, yours might be find the sample size, and it'll give you the population standard deviation. It might say that instead. So all I'm going to do is square root of 49 is 7. So I have 4 equals sigma over 7. Multiply both sides by 7. This is really ugly. So I have that my sigma equals 28. So all you're doing is just using your algebra with the formula to solve for a different variable. So that's all that problem is. But I know that this one has been one that confuses people every single term. That's why I go over this one. And there's one other one. So this one right here. It's the next question. So this one confuses people because the first one here says find the probability that a single randomly selected value is greater than 6.6. When we are using a single randomly selected value, we use our original standard deviation. You're still going to use normal CDF, but you're using the original standard deviation because you're looking for a single person randomly chosen. On the bottom one, now you're finding the probability that our sample will have a mean greater than 6.6. For this one, you use the new standard deviation and use normal CDF with the new standard deviation. So this one is our old way. This is chapter 7, the top one, and then the bottom one is chapter 8. So those are the two questions I get the most questions about through my messages. So before we go, while we're on recording, does anybody have any questions?
Yeah, can you clarify real quick what it is that we need to look for? Like the difference between the two standard deviations and how we know which one we're solving for. Can you clarify that for me real quick?
Okay, so when I'm looking for the probability that a one randomly selected individual has a characteristic. So I'm looking for one randomly selected individual. You're going to use the given standard deviation. So this right here. But this one right here, it says, what is the probability that I get a sample size of 88 and the mean of that sample size is greater than 6.6? That's looking when it gives you the sample size and it wants you to find the probability of a mean. That's when you use the new standard deviation, the sigma divided by square root of n. So the difference is the single randomly selected value and the sample size. Those are the difference between those. Is that what you were asking?
Yes, that's perfect. Thank you.
Okay, good. Any other questions while we're on the recording? And I'm going to stop the recording.